In this video, we'll be returning to the binomial distribution and talking about how some of the applications of the normal distribution can help us solve some complicated problems that we couldn't really do by hand with the binomial distribution, even after we got our formula for finding the probability for an individual x. So recall that we worked on the binomial distribution already in chapter 5. But remember when we had that greater than 3 problem, we were looking at the probability that greater than 3 teenagers exhibited whatever. That was kind of painful because we only had a formula to calculate what if the probability for exactly x equals blank. Even some of the exactlies are kind of tough, and we'll talk about a couple examples. Actually, real quick, if you want to try one by hand, go on and try finding the probability that exactly 50 heads are flipped if you flipped 100 coin flips. Like, just look at that one by hand, see how that works out. That's a pretty complicated problem, even though it seems like one that we should be able to do with that formula. And we can solve with the formula, it's just that the formula can be complicated. However, if our sample size is large enough, so again, think around that 30 number, the normal distribution can be used to approximate probabilities for a binomial. We're not going to talk about the details here, but this is directly an application from the central limit theorem. The problem is continuity. In that binomial, remember that was a discrete distribution. Remember that was covered in the discrete probability distributions. And the normal is a continuous distribution. So we have to correct for the fact that we're going from a continuous distribution to a discrete distribution, and this is called a continuity correction. Now the continuity correction is going to look really cumbersome, but I promise it makes sense, so stick with me a bit and try to pay as much attention as you can. So when we're looking at a direct x equals a number in the binomial, what we're going to have to use for us is a little bit less and a little bit more. Think the histogram bars. Remember when we had to make a little space on the bottom and the top end? That's exactly what's going on here. So if we're looking for the probability of x equals a for the binomial, and we're using the normal approximation, and the normal approximation, we're going to find the area in between a minus 0.05 and a plus 0.05. If we're looking for greater than or equal to a, we're going to bump a down a little bit and then be looking upwards. If we're looking for greater than a, we're going to bump a up a little bit and then look upwards. If we're looking for less than or equal to a, we're going to bump a up a little bit and look down. And if we're looking for less than a, we're going to bump a down a little bit and look down. Again, this is looking tough, but we'll have an example here that hopefully will help it make sense. So remember, we're in the binomial distribution world. So if we're talking about the binomial distribution, we know the mean, we know the standard deviation. We can easily calculate those from the quantity that, from the problem. The problem is knowing or being able to calculate the exact probabilities that we're interested in. All right, so the goal of these is just to include or exclude the appropriate range around the whole number. So if I want to include a and I'm going up, then I need to drop it down a little bit to go up. So I'm going to go to our picture here, and let's see if we can draw this out to help it make a little bit more sense. So we've got our normal distribution, and then we're using this to approximate a binomial. Now these binomials are going to look like little boxes. So these are going to look like a histogram kind of. And my boxes suck, I apologize. Now I'll just go for broke here. Why not? All right, something like this. Hopefully your boxes look better than mine do. This is a terrible looking graph, but whatever. Okay, so if I'm using the normal distribution, and let's say we're trying to do something bigger than this value. So this is my value here, and I want to go in this direction. Instead of just including half of the box, instead of just including half of the box, I want to make sure that I drop down a little bit to get to the full end of this box and then go up. So when I'm going up, to include this box. So this is the greater than or equal to. So when I'm going up to include this box, so up is greater than, include is the equal to, then I want to make sure that I drop down a little bit to include it. So that's where this minus 0.5 comes from. Minus 0.5 comes from. Now if this is just a greater than, I want to not drop down a little bit. I actually want to go up a little bit to make sure that my box is not included. So if I'm doing greater than, or my box isn't included, I want to go up. Oh, and I need to grab my... Nope, that's not working. Let's just erase this. So I was here, and then I dropped down a little bit to include the box. If I want to not include the box when I'm going up, I need to jump up a little bit and then go over. So this is where that plus 0.5 comes from, is from jumping up a little bit to go over so that I don't include that box. Now the tricky part is that when I'm going down, if I want to include the box, I actually have to jump up a little bit to include the box going down. That's why the direction changes. So when I'm going down for the less than or equal to, I want the plus sign, and it's opposite. And the reason that it's opposite from previously is because, again, when I'm going in the down direction, I need to go up a little bit to make sure I include the box when I'm going down. Now vice versa, if I'm going down and I don't want to include the box, then I need to jump down a little bit to make sure that I don't include the box. That's where this minus 0.5 comes from. So when you're looking at this, there is a long series of rules that you can look at, and they're listed in that table. But when trying to get this, I actually can't really remember those rules. To me, the intuition of when I'm going up, I want to drop down a little bit to make sure that I catch the whole box if I want the equal sign. If I don't want to catch the whole box, then I want to add a little bit to make sure I'm not catching any of the box when I'm going up. That intuition makes a lot more sense than this table does to me personally. So feel free to keep looking at this. Try to make sense of this table. Draw out a few cases of your own. Maybe draw out that graph that I was just working through to try and make sense of this. It's a pretty hard concept, honestly. So look at it, see how you feel, and maybe pause and go back over what we just talked about a couple times until you really feel like you got it. All right, so for our first example, we've got a baseball player's batting average. So this is the average number of hits that they get, 0.320. Find the probability that a player will get at most 26 hits and 100 times at bat. So note what's going on here, at most 26. So this is the most that they get. So in this case, if we had to do this by hand, we would have to do 26 and 25 and 24 and 23 and 22 and 21 and 20 and do it all the way down. Now that's just not reasonable to do by hand. So that's where this normal approximation is going to be really, really helpful. Now here we identify the number of hits at bat. So we've got 100 times at bat. That's our number of trials in. The probability of a hit at any time at bat is this batting average, 0.32. And then the probability of failing is 0.68. We can calculate our mean and our standard deviation, pretty straightforward. Now this is stuff that we did in the last chapter, so please review that if you're confused as to where these are coming from. And now what we're going to do is we're going to use the normal approximation to try to find this probability of getting at most 26. So most 26 means that we want a value that is less than or equal to 26. The equal to, because 26 is a possible option. So we have less than or equal to 26, and the continuity correction, because we want to include 26, is to go up by 0.5 when we're going down. So go back on that table, check to make sure that you can understand where this is coming from. The proper continuity correction is to go up by 0.5 when we're trying to go down to include that value of 26. All right, so now we're going to solve for the z-score. Now note, because this is an individual, we're going to be using this older z-score, not the central limit theorem one. Now we calculated the mean 32 and the standard deviation 4.6648 from the previous data. This 26.5 is the value that we're interested in, so negative 1.1790 is our z-score. And we're looking for at most, so we want everything to the left of this. This is the biggest number that we want to see. So looking at the table, the area to the left is 0.1190. That's what we're interested in, is the area to the left. So the probability that it is less than this 26.5 at bats is 0.1190. It looks like I have a bit of a typo here. This should be the probability that x is less than the 26 at bats. So again, even though we've used the continuity correction, the interpretation is still the interpretation of the binomial. So this binomial interpretation is what we're going for. This is at most 26. We're not going to use 26.5 in our interpretation. Is about 11.9%. That's the probability that this individual will get at most 26 hits and 100 at bats. Now we can calculate this using that 26, 25, 24, 23, 22, doing all those calculations by hand. Now that's not recommended. We're going to use software for this. And you'll see that even though this normal approximation isn't doing all that work, we're cheating a little bit. It's very, very close to what this is recommending. So we've got 0.119 versus what software says when it does it exactly, which is 0.118. So very, very close for a fraction of the work. All right, so in this case, we're looking at a bowling league. We have 10% of the members of the bowling league are widows. So if we have 200 bowlers sampled randomly, what's the probability that 10 or more will be widowed? Now note what we would have to do here. We'd have to find the probability of 10 or 11 or 12 or 13 or 14 or 15, all the way up to 200 if we were doing this by hand. That sounds very, very, very tedious. Instead, go on your own and give this a shot using the normal correction. Use that table as much as you need to. All right, coming back, so we've got 200 sample size. The probability is 10 for any individual that they are widowed, and then the probability that they're not widowed, 90%. We can calculate our mean and standard deviation, and again, we're going to need those for the z transformation, or the changing these to a z-score that we're going to do in a bit. Now we're looking for the greater than or equal to probability. So remember that when we're looking for greater than or equal to 10, we have to drop this down by 0.05 to make sure that we grab that 10 bar in our binomial distribution. So again, go look at that table for the continuity correction. Make sure you're following this, but we need to drop it down by 0.05 to account for the continuity correction. So we're going to be using this this 9.5 number when we use our z, when we calculate our z-score. So we're going to change this 9.5 number into a z-score by subtracting the mean divided by the standard deviation. Now, when we calculate this, the tabled value is 0.0066, so there's about 0.66, less than 1% is on the left here. But remember, we're not looking for the area on the left, we're looking for the area on the right. So we're going to do 1 minus that value, 0.9934. There's a 99% chance that at least 10 of the bowlers are widowed if the underlying population is at 10%. And again, when we compare this to software, we see that this is a very, very close approximation. But again, this beats doing 191 probabilities of that p of x equals n choose x times p to the x times q to the n minus x. We'd have to do 191 of those to get this probability exactly. So this normal approximation is very handy. All right, now let's try an exact probability. You can think of this one, or another one you could try is the probability of getting exactly 50 heads out of exactly 100 coin flips. That's a really hard one to do via the old equation. This one you can try, so go on and pause, give this one a try for an exact probability using that finite population correction factor. All right, coming back. Here we've got 300 drivers. Each of them has a 6% chance of reading the newspaper. Note that because we have a success failure, you read the newspaper, you didn't. Note we have a fixed number of trials. Two options, the probabilities stay consistent, that this is a binomial. So this is a good thing to think through too. Is this a binomial case or not? In this case it is. The probability of success of reading a newspaper, that's not really success, but whatever. Probability of reading a newspaper is 0.06. Probability of failure is 0.94. We can calculate our mean and standard deviation quickly. Now for the finite population, or excuse me, not the finite population, the continuity correction factor. Remember that when we're doing an equals problem, exactly 25, we need to bump down a little bit and up a little bit to kind of create that bar that we're interested in. So actually this becomes a harder problem because we have to do the score for 24.5 and the score for 25.5. So we've got two z-scores, one for 24.5, one for 25.5. We calculate both of these, and now we're finding the area in between them. So looking in the table, the Z1 value is 0.9429. It's the smaller one. The bigger one's 0.9656. And then we subtract these two to get the probability of exactly 25 drivers. So that's going to be 0.0227. About 2% of individuals, there's about a 2% chance of exactly 25 people in the sample reading the paper while driving. And again, looking at this in software, we see that this is about 2.26% chance instead of a 2.27% chance. So very, very, very close to what we would have otherwise. This takes us to the end of our normal approximations of the binomial distribution. I highly encourage you to continue, maybe rewatch these slides a few times. That continuity correction factor is kind of a toughie, it really is. So feel free to go back and look over this as many times as you need to. Try out a few problems in the textbook. This also takes us to the end of chapter 6 and the end of the material for your test coming up. So as you're reviewing, please make sure to rewatch these videos, try out some of the problems that we've done in our notes, try out some problems in the textbook, try out some of the problems that are online in order to prepare for this. I think chapter 6 is on the homework application, so feel free to use the homework application to prepare specifically for this chapter. Though I'm not sure if it has much of the binomial stuff. I think that's going to be more in your textbook. Also, don't forget that your journals are going to be up and due, so please make sure you get a chance to do those. For our next video, when we get there, this is again after our second test, we'll be looking at confidence intervals, which are really, really useful statistical procedure. In fact, we already did some of those earlier when we were first talking about the normal distribution. So look forward to having that